we will learn about ionic equilibria, and in this topic we will look Arrhenius theory and Oswald's dilution law. First, we will look about what is ionic equilibrium. The ionic equilibrium is related to the equilibrium between the ions and its undissociated molecule. So in this, the Arrhenius theory is also important. So different substances like salt, acid and the bases are dissolved in water. They produce the positively and negatively charged particles called the ions. Means substance producing the ions, cations and anions when dissolved in water is known as an electrolyte. So according to the Arrhenius theory of dissociation, an electrolyte when dissociate in water to form ions, these ions remain in the state of equilibrium with its undissociated molecules. So this is an electrolyte known as the AB molecule, and it undergoes dissociation to form A plus ion, that is cation, and B minus ion, that is anion, in dissolved form. So there exists between an equilibrium between the dissociated ions and undissociated molecule, and this state is known as ionic equilibrium. Different electrolytes undergoes different extent of dissociation measured by the degree of dissociation, that is the alpha, and fraction of electrolyte undergoing the dissociation is called degree of dissociation of electrolyte, means alpha. So based on this Arrhenius theory of dissociation, there are two types of electrolyte. One is strong electrolyte and other is the weak electrolyte. We will look the difference between the strong electrolyte and the weak electrolyte. First difference, the substance that completely dissociated into ions when dissolved in water is known as the strong electrolyte, and the substance that only partially dissociates in ions when dissolved in water is known as the weak electrolyte. The degree of dissociation means alpha of strong electrolyte is very high, while the degree of dissociation of weak electrolyte alpha is low. Strong electrolyte is producing more number of ions in solution, so it is good conductor of electricity. Weak electrolyte is producing less number of ions in aqueous solution when dissolved in water, is poor conductor of electricity. The example of strong electrolyte is sodium chloride, hydrochloric acid, potassium hydroxide, etc. They undergoes complete dissociation in water while the alpha value is very high. The example of the weak electrolyte is acetic acid, ammonium hydroxide. These compounds are known as weak electrolyte because it undergoes poor dissociation in water and their alpha values are very small. So based on this knowledge of Arrhenius theory of dissociation, we will go for the Oswald's dilution law. The Oswald dilution law, according to the Arrhenius theory of dissociation, an electrolyte AB when dissolved in the water to form ions A plus and the B minus, this ion remains in state of equilibrium with the undissociated molecule, and it is represented by the chemical equation for electrolyte AB. If the C is original concentration of AB and alpha is fraction of AB undergoing dissociation, means degree of dissociation of the electrolyte AB, then this AB when dissolved in water, it undergoes dissociation to form A plus ion and the B minus ion. Before the dissociation, means at time t is equal to 0, C is the original concentration of AB in moles per liter. But when the dissociation happens, after dissociation, the alpha fraction of the AB electrolyte is undergoing the dissociation. So C into 1 minus alpha is the remaining concentration of AB electrolyte in moles per liter at time t, while the concentration of A plus ion is alpha C. Similarly, the concentration of B minus ion is alpha C. So, according to the Oswald, the law of mass action can be applied to the ionic equilibria like chemical equilibrium. So, according to the law of mass action, under equilibrium condition, the rate of reaction is directly proportional to the concentration of reactant. In the forward reaction, the reactant is AB. So for forward reaction, rate of forward reaction is velocity constant or rate constant into concentration of AB electrolyte is equal to K1 into C in bracket 1 minus alpha. This is the rate for forward reaction under equilibrium condition. For backward reaction, the rate of backward reaction is equal to the velocity constant K2 into concentration of A plus ion into concentration of B minus ion. So it is equal to K2 into alpha C is equal to K2 into alpha square square. So with the help of law of mass action, we determined the rate for forward reaction and rate for backward reaction. So after dissociation, what happens? There is exist equilibrium between the dissociated ions and the undissociated electrolyte, and at equilibrium the rate of dissociation of electrolyte is equal to the rate of recombination of ion. The rate of dissociation of electrolyte AB is forward reaction, while the rate of recombination of ion is the backward reaction. So at equilibrium, the rate of forward reaction is equal to rate of backward reaction, means K1 into concentration of AB reactant is equal to K2 into concentration of the A plus and the B minus ion. So the rate becomes equal under equilibrium condition. So substituting the value of corresponding concentration for reactants, we get the K1 into C in bracket 1 minus alpha for forward reaction and K2 into alpha square into square for the backward reaction. So here we are separating the concentration term and the rate parameter. On separating the rate parameter and the concentration parameter, we get the K1 upon K2 is equal to alpha square square divided by C into 1 minus alpha. But the ratio of the velocity constant for forward reaction and for the backward reaction is the dissociation constant Kc. So we can write the dissociation constant Kc is equal to alpha square C square divided by C into 1 minus alpha. On further simplifying this equation, the C is cancelled. So we get the dissociation constant Kc is equal to alpha square C divided by 1 minus alpha, and this is numbering, this equation is numbering as 1. We are substituting the value of concentration. C is equal to the number of moles divided by V, means if the 1 mole of electrolyte is dissolved in V liter of solution, then C is equal to 1 upon V, where V is called the dilution of solution in terms of the volume. This substituting the value of equation C in equation 1, we get the Kc is equal to alpha square divided by 1 minus alpha into V, and this equation is known as the Oswald dilution law. So in Oswald dilution law, it is showing the relationship between the degree of dissociation and the dissociation constant. So equation which shows the correlation between the degree of dissociation and the dissociation constant with the dilution is known as the Oswald dilution law. So this is the equation for Oswald's dilution law. We are comparing the equation for the strong electrolyte and the weak electrolyte for Oswald dilution law. So first, for the weak electrolyte, the value of alpha is very small as compared to the original concentration of electrolyte. So the degree of dissociation means alpha is neglected as compared to C. So the factor 1 minus alpha into V is equal to V. So putting this value, the dissociation constant becomes Kc is equal to alpha square divided by V, while alpha square is Kc into V. Therefore, alpha is equal to in square root Kc into V. Alpha is equal to K dash into square root of V. So finally, we get the degree of dissociation is directly proportional to the square root of. In case of strong electrolytes, the alpha is very high, so it cannot be neglected. So for this, the Oswald dilution law equation remains the same. This is original equation of Oswald dilution law. So further simplification or solving equation for alpha will give us alpha square is equal to KCV minus alpha KCV. So in quadratic form, it takes alpha square plus alpha KCV minus KCV is equal to 0. So here we have seen the Oswald dilution law equation for weak electrolyte and the Oswald dilution equation for the strong electrolyte. So we seen that the degree of dissociation of weak electrolyte is directly proportional to the square root of dilution, where the K dash is the proportionality constant. But in case of the strong electrolyte, Oswald dilution law fails completely when applied to the strong electrolyte. So student, here we seen the Arrhenius theory of dissociation, Oswald dilution law in this video.